Here's the picture from the problem. So I'm going to draw free body diagrams for both of these blocks. So for the top one, we're going to have m sub 1 g, because I'm calling this one number 1 and this one number 2. So we have m sub 1 g downward. We have a normal force going up. This force here, F, is pulling on the top box, so I'll put that this way. And then it's accelerating, but we have this friction here in between the two boxes. And the friction is static, and it's going to act on both boxes. So it's going to act backwards on the top box. So there we have the static friction. Now, for the bottom box, we have m sub 2g going down. We have a normal force, and now I realize I need to label these normal forces separately. This will be normal force number 1, and this is normal force number 2. Okay, so this one has friction on both surfaces. It has kinetic friction on the bottom surface and static friction on the top surface. So the static friction is what's pushing the bottom box forward. So static friction is going to go to the right, which makes sense because it's an action-reaction pair with that one. So they should be pointing in opposite directions. Then we have kinetic friction going to the left. This is slowing the box down because of its interaction with the table. Okay. Now, the problem told us M1 and M2. It told us the two coefficients of friction, mu sub s and mu sub k. And it's asking us for the time it takes to travel a certain distance x. Well, if it starts from rest, then I know I can find the time if I have the acceleration. So, because I have this equation, x equals 1/2 at squared. So if I know x and I can find the acceleration, then I can calculate the time. So I'm going to use these free body diagrams to find the acceleration. I did, however, leave off one force. Did you notice it? The bottom box is what's holding up the top box. So this normal force number 1 that was in this free body diagram, it needs to be over here too and pointing downward because that's part of an action-reaction pair as well. So now I think I have them all of the vectors there. So now I'm going to write my equations. And in the x equation here, I have my force F, which they didn't tell us what it was, minus the static friction. And that's going to be equal to ma because this block is accelerating to the right, and it's m1a because this is block number 1. In the y direction, I have normal force number 1 minus m1g equals 0. Now this talks about the static friction, and the static friction is on this surface here, so it has to do with this normal force. So that means my static frictional force is going to be our coefficient of static friction times n number 1. All right. Now for this equation, for this diagram, I get these equations. I have the x equation, static friction going to the right, kinetic friction going to the left, and that has to be equal to m2a. Now, how do we know that this a is the same as that a? Well, because they're staying together. Right, so they were talking about the minimum time you could get it across the table and have them still stay together. So I know those two A's are the same. Then in the y direction, I have normal force number 2 minus normal force number 1 minus m2g equals 0 because it's not moving in that direction. And then the sliding friction is happening on this surface here, which has to do with this normal force number 2. So sliding friction is mu sub k n2. Right? And those are all my equations. And all I need to do is find out what the acceleration is. So I see the acceleration here in this equation, and I like that because I know I like this equation better than this equation because I'm really suspicious of this force F that I don't know what it is. They didn't tell me, they didn't ask me for it, so I want to stay away from that equation if I can. I want to go to this one. And so what I think I need to do is find out what f sub s equals and find out what f sub k equals and plug it in there and see if that'll work. So I come back over here to look at f sub s. Well, it's mu sub s times normal force number 1. But I can see from this equation that normal force number 1 is equal to m1g. So that's something I can use. I can plug that in there because I know mu sub s, I know m1, and I know g. So then I come over here and look at f sub k. And I see to get an expression for f sub k, I have mu sub k, I need something for n2. So this equation tells me that n2 is equal to n1 plus m2g. But this equation told me that n1 was equal to m1g, right? So n2 is equal to m1g plus m2g. And that means that f sub k is equal to mu sub k, parentheses, m1g plus m2g. So now I'm going to put that all together from that equation. So from here, static friction is mu s m1g minus this thing, mu sub k, parentheses, m1g plus m2g equals m2a. Now, this is an equation that has m1 and m2 in it. It has the two coefficients of friction, which we know, and g. So we can solve this a equals, and you'll get a number. Then you could just plug that into this equation and find out that the time is equal to the square root of 2x over a. You know what the x is from the problem, and then you can do the calculation.